Okay, chapter 5, probability. So this chapter is going to be kind of in stark contrast to what we have done up until this point in Math 2. This one definitely takes a sidestep from the algebra that we've basically leaned heavily into throughout this semester. Okay, chapters 1 through 4 lean very heavily into functions, solving equations, doing so algebraically. And in some cases, a little bit of geometry has been folded in there, even if it's just in small techniques and stuff. But it's a heavy algebra semester. This chapter is going to feel very, very different than that, which for some of you may be very good news. But probability is a far more abstract concept. But here's the good news. Probability and statistics, which will be closely tied to this, even though we're not going to get deep into statistics within this chapter. But probability in and of itself is one of the most common forms of mathematics used for everyone, right? You'll be familiar with some of the concepts at the very least, and if nothing else, you'll definitely be dealing with some very familiar type of examples. Okay, lots of very familiar applications for this that everyone will use regardless of what career you end up in. So what is probability? Probability fundamentally has to do with the likelihood of something happening, okay? Typically, when we deal with all the algebraic stuff in the past, that is used in some way, shape, or form towards trying to make educated guesses and anticipate outcomes and stuff like that. Algebra is definitely instrumental in solving those things, just like we used it for quadratics in the last chapter. Probability is more of a general concept of simply determining likelihoods of some sort of outcome happening. And so how is a probability measured? Okay, the measurement is typically between some value between 0 and 1. 0 meaning that it definitely will not happen. There is a 0% chance of something happening. And 1 or 100% chance of that thing occurring or that thing will happen, right? Certainty at 100% or 1 value and an absolute certainty of not happening at 0 or 0%. Okay, and it'll fit in between there. Despite what any of your sports coaches may have said, it is impossible to, in fact, have 110% possibility of something happening. Okay, that does not happen in mathematics. Right now, it can be applied in different usages. It's not like that just doesn't exist. But within probability, as far as likelihood goes, it will be some decimal that can be converted into a percentage that will fall between 0 and 1. So that's the type of thing that we're going to be seeing throughout this chapter. So here in section 1, we're going to focus on the very, very fundamental aspect of probability, and that's discovering sample space, right? So sample space. Sample space refers to the set of all possible outcomes, okay? And what kind of outcomes we're talking about? Like, all right, some event happens. What are all the possible outcomes that can stem off of that event? Okay, some of those events are very, very simple. I've listed some of them right here that many of us are more than familiar with. For instance, flipping a coin. That is an event, right? And so you're going to hear a lot of these terms quite a bit throughout these chapters, so just start getting used to them. So an event of flipping a coin, which sounds like a very boring, lame event, but in any case, it is an event. There are only a limited number of outcomes that can happen. It will either land heads or tails. At this point, usually I get some smart-ass students saying like, well, what if it lands on its side? Yeah, okay, fine. But for the sake of this theoretical probability right here, we're going to talk about very, very definitive solutions. Namely, when I flip a coin, I'll either get heads or tails, right? So the sample space of flipping a coin has two possibilities, two outcomes, right? Rolling a 6-sided die, and the reason I go through the effort of writing this, for many of us, we're only familiar with 6-sided dice, but if anyone is familiar with like Dungeons and Dragons or any of these other hyper nerdy type of things to do, and I don't say that nerdy like in a judgmental way, I am definitely a nerd, but I mean, there are other dice out there that have different numbers of sides. Not every dice involves 6 sides. Again, we're most familiar with the 6-sided die. This will be pretty much the type of thing we'll be dealing with in this chapter. But for a 6-sided die, there are in fact 6 outcomes, right? Because there are 6 sides, and There's like a designation for each of the sides with the number of dots or the value on that side, right? For a deck of cards, right? There are lots of different decks of cards out there, but what we'll consider are a standard deck of playing cards, which this one tends to be like the measurement that, for whatever reason, not a lot of people are super familiar with. You may be familiar with a deck of cards in general, but it is useful to know some of these things. So particularly for this little piece right here, you might want to highlight this little description right here, because again, for many of us, you may have played with playing cards before, but it will be important to understand like what are the actual numbers entailed with that. So in a standard deck of playing cards, there are in fact 52 cards. 52 cards. All right. Now, those 52 cards include 4 different suits, right? Hearts, diamonds, those are the red cards, then spades and clubs, the black cards, right? And if you are less familiar with cards, these will be things worthy of putting like in the margins and stuff, because you will be asked some questions about a standard deck of playing cards, and it's useful to have some of these things down. So there are 4 suits are what they're called, 4 different types of like groups of cards within a standard deck. And each of those suits has these values on it, right? Many of us, again, are familiar with these. You have your face cards like the king, queen, and jack. And then you have the number cards, numbers 2 through 10, right? And there's not a number 1 card. Instead, they have the ace, okay? And we can debate about the actual value of an ace. It depends on the type of game you're playing, whether ace is ahead of king or if ace is a 1 in this case. For our intents and purposes here in this class, we're simply going to be caring about the value on that card, okay, rather than what it's worth and that sort of thing. So again, the reason I'm emphasizing a little more time on this standard deck is, for whatever reason, I get a handful of students that aren't as familiar with the standard deck, and so it's worthy of knowing these numbers, that there are 52 total cards. Of those 52 cards, there are 4 different suits. Each of those suits has 13 values on it, simply by dividing 52 by 4. So there are 4 kings, 4 queens, 4 jacks, 4 tens, so on and so forth. Okay. And again, the names of those suits are hearts and diamonds, which are the red ones. And then the black ones are spades and clubs. Okay. So why did I go through describing that? These are the ones we're going to be dealing with the most, particularly in this section where we're talking about simply counting a sample space. Knowing the values of those sample spaces will be important. But here's why I also want to talk about what I have written here in the margin. Theoretical probability. Theoretical probability. So what does theoretical probability assume? And quite frankly, it's actually worth discussing. Like almost all of math that you have done up until this point has been theoretical. In real life application, quite frequently things are far more messy, right? That's what we would, and when it comes to probability, there's another type of probability called experimental probability. And we'll talk a little bit about that moving forward. But theoretical probability is where we begin by determining possible outcomes, right? It first assumes that all things are equal, okay? Particularly when it comes to flipping a coin, right? When you flip a coin, we're going to assume that there is an equal likelihood of you flipping heads as it is to tails. Now, interesting fact, it is actually in experimental form. If you were actually to do this experiment, you would very likely find that you would actually get tails a little bit more often than heads. It would take probably millions of iterations of doing this in order to find this out, but you would have an ever so slightly advantage of choosing tails. Why? Because if you were to break down at a very, very small scale, a quarter, for instance, and look at the material on it, because on the heads side of a quarter, the face of George Washington is a little bit raised from the surface of that quarter, as many of us are familiar with, the amount of material of that metal that makes up his face is ever so slightly more than the amount of material that makes up on the tail side, the eagle and arrows and stuff. The amount of material for the face is just ever so slightly more than the tail. And because of that, it is slightly at a minuscule level, more mass on that side. Because of that, it typically will want to be the side that lands down first. And so we're talking at a very, very, very molecular level at that point. And so when it comes to flipping a coin, we're going to assume that there is an equal chance of flipping heads as it is tails. right? And an example of doing experimental probability would be like, all right, you perform an experiment, you flip a coin 100 times. It's probably not 100. It's probably not likely that you would get exactly 50 heads and 50 tails. You would probably have like one or two more to one side or the other for whatever reason, because of how you flip the coin, whether you put an emphasis, whether you're catching it and slamming it down your hand, like how far it's falling. There are lots of different variables that go into an actual real life application of this. So again, theoretical probability will assume all things are equal. So if you flipped a coin multiple times, you'd flip it the exact same way every single time. There would be no other influences that would affect the outcome. Okay. When it comes to rolling a die, again, interesting fact here. If you did not know this, that the 6 side of a die actually has ever so slightly less mass than the 1 side of the die, because each of those little dots tends to be a little bit of a carved out section of that die. And so the 6 side would have ever so slightly more, 5 extra little dots taken out than the 1 side. And so because of that, it would have a little bit less mass on that side than it would on the 1. And so technically the 1 would want to fall down first. Those are all hyper specific, very, very closely analyzed things that do play an effect in the grand scheme of things. If you were to roll a dice 1,000,000 times, you would find these slight variations. But again, we'll assume all things equal. There's an equal chance of rolling a 1 as there is a 4, as there is a 2, as there is a 6, so on and so forth. In a standard deck of cards, we're not going to have stacked decks. Okay, we're not going to have these are standard 52 card decks. There are 4 suits. There are going to be 13 of each card. It's not like you're going to have a deck that's completely filled with kings or 5s or aces or whatever. Okay, these will be standard decks. No cheating involved. Okay, that's worth pointing out because again, there are going to be exceptions. I always have that smart ass student that's like, well, what if I like put an extra 10 in that deck, or I removed one of the 2s, and it's like, okay, well now you've just fundamentally changed the outcomes. Okay, so sorry, I got off a little bit of a tangent there. Let's get back to this actual section. In that, all right, our first job, the most fundamental part of determining probability, is determining a sample space. How many possible outcomes are there? In each of these cases, for flipping a coin, there are 2 possible outcomes. Rolling a 6-sided die would have 6 possible outcomes. Drawing a card from a standard deck would have 52 possible outcomes. And these are examples of some of those results. Okay, so each of those individually is a pretty simple thing to count as far as a sample space, how many outcomes can exist. But let's get a little bit more complicated. What happens if we were to have multiple things happening at once? All right. And so as with most mathematical things, we're going to add in a couple of wrinkles. We're going to add in some complication. Okay. So what happens if I were to determine the sample space, or again, the total number of outcomes for a little bit more complicated scenarios? Instead of flipping a single coin, what happens if I flip 2 coins? How does that change the sample space? Okay. And so this little asterisk point right here will be very, very important to understand. For multiple samples, and what I mean by multiple samples is multiple events are happening. Okay, in this case, flipping 2 coins, that's technically 2 different events. Flipping coin number 1, flipping coin number 2. You flip 2 coins and roll a 6-sided die. So flipping first coin, flipping second coin, and then rolling a 6-sided die, that's 3 events happening at this one. Okay, as you add in more events, here's what you're going to be doing. You're going to multiply each respective sample space together. And I'll show you why right now. So let's do these 2 examples to keep it simple. All right, so here we are determining what is called sample space. And in some cases, they'll actually have you write out what those sample spaces are. So for instance, our first example is flipping a coin twice, or flipping 2 coins, or whatever. Right. So we're flipping 2 coins. Let's determine the sample space. All right. I'm going to use 2 different colors here to help us determine this. So coin number 1, I have 2 possible outcomes. I could flip a heads and I could flip a tails. That's coin number 1. Coin number 2, nothing different here. I would just also be able to flip a heads, and I would also be able to flip a tails. Okay, so each of these represents an event. I have the possibilities of each. Coin number one, I could flip a heads or a tails. Coin number two, I could flip a heads or a tails. In each of these cases, I have two possible outcomes. Simple enough. So according to that little asterisk point that we made there, if I have two possible outcomes here, I would multiply by however many outcomes the other event had. In this case, I would have a total of 4 possible outcomes. Flipping 2 coins, I could have 4 possible outcomes. So if you're not convinced, I'm actually going to write that out. There are only 4 possible outcomes. Might as well write them out. And there's a reason I color coordinated this right now. So here are those 4 possible outcomes. I could have flipped a heads first with my first coin. Okay. Well, if I flipped a heads with my first coin, I could flip a heads with my second coin or a tails with that second coin. So I could have heads, heads, or I could have, again, that same heads first, and I could have a tails second. Great. So those are 2 of the 4 outcomes, and that's if I flip the heads first. Now, again, the reason why I end up doing this multiplication is because if this is one possible outcome, either of these will work. So that's that outcome times the 2. And then I move over to my next outcome. Also, either of these are an option. So for instance, instead, I could have flipped a tails first and then a heads second. Or I could have flipped the tails first and then a tails second. There are my 4 different possible outcomes determined there. This is what we would call the sample space. These are the actual every possible combination that can exist with flipping 2 coins. Okay, and that's just simply how it's determined. The simple thing to understand here, what you'll be asked to do for your first few problems in this assignment is it'll simply say determine the size of the sample space. So when you're flipping 2 coins, right, coin number 1, 2 outcomes. Coin number 2, 2 outcomes. Just multiply those values together. The size of my sample space is 4 large. Okay. If they ask you to actually identify and write out the sample space with something like this, that's not terribly difficult. There are only 4 possible outcomes here. That would be how you might write it out. If I flip a heads, I could either flip heads or tails next. Or if I flip tails, I could either again flip heads or tails next. So that would be how it's written out. Simple enough when there are only 4, but you're going to see these sample spaces get awfully large very quickly. So now the second example here. Okay, we're still asked to determine sample space. For example part B right here, now we're flipping 2 coins and rolling a die. A 6-sided die specifically. Okay, so technically here again, there are now 3 events happening. 1 coin, 2 coin, and a die being third. So just to kind of show us again the sample space, for coin number 1, I have 2 possible outcomes, heads or tails. For coin number 2, again, heads or tails are my results. And then now event number 3 being rolling the 6-sided die. In this case, I can't roll a heads, so to speak. Instead, now I have the possibilities of 1, 2, 3, 4, 5, or 6. And so back to what this question is asking for, determining the actual size of this sample space. In this case, again, I would just multiply the sample spaces together. There are 2 possibilities, 2 outcomes for coin number 1, multiplied by 2 possibilities for coin number 2, multiplied by now 6 possibilities for rolling a die. And so if I were to multiply these together, 2 times 2, that gives me 4. That 4 times 6 gives me a total of 24 total outcomes. Now that's a far larger sample space than our last one. And here's how you could determine, and if it did ask you to write them out, here's how I would go about doing it. Okay, I would start with the fact like, all right, outcome number 1, I could flip heads. And so with that heads, I could either get heads or tails. And then I could have heads, heads, 1, 2, 3, 4, 5, 6. I could have heads, tails, 1, 2, 3, 4, 5, 6. Okay, now I'm done with that guy. I could have tails, heads, 1, 2, 3, 4, 5, 6. Tails, tails, 1, 2, 3, 4, 5, 6. At that point, I now have the full 24. Okay, so technically you only have to like work your way through this guy through each of them. You don't have to like then move over here and over there, that sort of thing. So then you'd get repeat values, but that's where the 24 comes from. At a more simple level, how would you determine the size? How many outcomes for event 1? How many outcomes for event 2? How many outcomes for however many events you have after that? Multiply those values together. There's the size of your sample space. Okay. So that's a very fundamental aspect of determining probability, because if I know how many possible outcomes there are, when it comes to determining probability, here is how that is applied. So let's jump back to the notes. All right. So probability. Fundamentally, this is what probability means. Here's the formal definition. Okay, the textbook uses this wording. You can kind of fit in whatever wording works for you, but essentially they say the number of favorable outcomes. Okay, and what does it mean by favorable? Essentially, when you're asking what's the probability of something happening, a favorable outcome means that something happened. For instance, what's the probability that you roll a 4? Okay, the favorable outcome would be you be simply rolling that 4. How many ways are there to roll a 4? Okay. And in some cases, there will be more than one. So for instance, I could reword that to say at least a 4. Okay. So pay attention to the difference of that wording. What's the probability of you rolling a 4? In which case there's only one way to roll a 4, and that's by simply rolling a 4. Or what's the probability of you rolling at least a 4? We tend to see that one when it comes to like board games, right? If I roll at least a 4, I'll get to past this point or whatever it might be. Right. So there are actually a couple favorable outcomes to rolling at least a 4. You could roll a 4 or a 5 or a 6. So in that case, there'd be 3 favorable outcomes. Okay. But when it comes to probability, you'll have favorable outcomes or successful outcomes. And then this is representative of a fraction. So that numerator represents the favorable outcomes. On the denominator, we're just talking about the possible outcomes that exist, the total possible outcomes. That denominator is where the sample space that we just talked about comes from. Okay, because if I can determine a total sample space, that becomes the denominator, or the thing I'm going to compare the favorable outcomes to. All right, so the successes would end up on the numerator. The total possible, or the total sample space, would be my denominator. Okay, for instance, right here, here's a nice illustration of that. What's the probability of drawing an ace out of a deck of cards, a standard deck of cards? Again, we're going to assume theoretical probability here of all things being equal, not some weird deck, or like what's the probability of drawing an ace out of a deck of Uno cards? Okay, that can't happen. Anyway, so what's the probability of drawing an ace out of a standard deck of cards? All right, so again, referring to my probability here, the denominator is going to be total possible outcomes. So when I'm drawing a card out of a deck of cards, it's going to be useful to know, well, how many cards am I drawing out of? For standard deck of cards, like we saw at the top of our notes, there are 52 cards. So my denominator will be that 52. Those are the total possible outcomes. There are 52 unique cards in a deck of cards. So favorable outcomes would be like, all right, what's the probability of drawing the ace or an ace, right? So in other words, it's asking, well, how many possible ways are there to draw an ace? How many aces are in a deck of cards? And again, here's where it comes in useful for those that are less familiar with the deck of cards to understand this, that in a deck of cards, there are 4 of each card. So there's the ace of hearts, then the ace of diamonds. Those are the red aces. Then you have your black aces, ace of spades, and then ace of clubs. There are 4 total aces in a deck of cards. So how many ways are there to draw an ace? It doesn't tell me anything further about that ace. It's just an ace. Okay, there are 4 aces out of 52 cards. So from a probability standpoint, that would be my fraction, 4 over 52. Now, one thing you'll have to be used to in this section, in this chapter, will be reducing fractions. So I would reduce this. 4 goes into both 4 and 52, and it reduces down to 1 out of 13. So that would be my finalized probability right there, 1 in 13. If I wanted to convert that into a percentage, and I want to know, like, what's the percent chance I happen to draw out an ace, which tends to be a popular way to express that. This fraction is also technically a division problem. 1 over 13 can also be read as 1 divided by 13. If I were to do that in a calculator, it would spit out this decimal, 0.077. And again, this will be something that you'll want to get used to, is converting this decimal into a percentage. I would move the decimal point twice, and that would come out as 7.7%. If I showed a deck of face down cards and I was like, what's the probability that you would select an ace, any ace? There's a 7.7% chance that you would select that ace, an ace. Okay, pretty low probability, but not impossible. Okay, so I think that's where we'll stop for today. We'll jump into some probability examples tomorrow to wrap up this section, but I'll go ahead and stop recording